But if I want to find the partial derivative with, we often abbreviate with respect to as WRT. That just means with respect to. With respect to x, we should be able to write it as either del f del x, which is the thing you're saying he makes look kind of like a 2, which I can kind of see that, right? If you're not super careful, I could see making it look kind of like that, which is kind of terrible. Okay, sure. All right. Or you should be able to write it as f sub x like that. Either way, that should be perfectly fine notation. So in this case, if I'm going to find del f del x, well, I'm looking at this function of x and y, and I'm seeing something with x's times, I'm treating this like a constant. Something without any x's also, it's just a whole constant by itself, and something with just x's. So here, I'm going to take the derivative of x to the 5th and get 5x to the 4th. I'm just going to leave the y squared alone. It's a constant multiple. And constant multiples, what do? I like to say they hang out. Constant multiples hang out. So if you have a function times a constant, that constant hangs out. Just I would use slightly different language. I would say you're taking the derivative with respect to x. Right, but we're pretending we're thinking of x as the variable and everything else is the constant. And yeah, so just to kind of, well, we'll come back around to that. So here, the derivative of 4 sine of y cubed, well, since it's not multiplying any x's, what's its derivative going to be? Yeah, because right, as far as x is concerned, this whole piece here is a constant. And its derivative of a constant is 0. Right? We're asking, how is the function changing as x changes? Well, this piece here, as x changes, this doesn't do anything. It stays constant. So its derivative is 0. Over here, the derivative of 6 e to the x squared. So I want to point out, just like here, when we take the derivative of x to the 5th times y squared, the y squared constant hung out. Here, the derivative of 6 times e to the x squared, the 6 that's a constant is going to hang out. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I want to really, really stress, as far as x is concerned, 6 multiplying by 6 and multiplying by y squared, kind of the same effect. They're both constants, and those constant multiples just hang out. Whereas constants on their own that aren't multiplied by the variable we're differentiating with respect to, they end up being 0. Let's look at the partial with respect to y. So we take the partial with respect to y. So now I'm looking at my original function and I'm treating x like the constant and y like the variable. So here the derivative is going to be, well, the x to the 5th is going to hang out, and the derivative of y squared is going to be 2y. Here, the derivative of 4 times sine of something, well, right, that is a variable. So now it's going to be, well, 4 times cosine of my stuff times what? Exactly. Plus, what's the derivative of this going to be? Right. And then maybe we'd simplify. I probably wouldn't simplify, but right, you could simplify a little bit. So let's back up a second just to kind of explore that limit idea, just to make sure he might, I don't know, he could ask something about it, I suppose. So here's really the idea. But let's look at a simpler function. Let's say we have something that's not too terrible to take the partial derivative. Let's say we have f of x comma y equal to 5x squared y to the 3rd. Sure, it's gonna be a little terrible depending on what I decide to do, but we'll figure it out. And I want to find the long way del f del x. Now we know that the answer should be 10xy cubed, right? The short way, or the fast shortcut way, right, is to say, oh, del f del x, wow, that's terrible, is going to be 5 times 2x times y cubed, which is 10xy cubed. But we're going to do the long way. We're going to use the limit definition. So whenever you're taking a derivative, of a function of one variable or a function of two variables. You're just saying, well, I'm really asking what's happening as my independent variable, in this case, x, as x changes a little bit. What happens to the slope? So we're going to say, okay, that's going to be the limit as h approaches 0. What's changing? Is x changing or is y changing? X, because I'm taking del f del x. So I'm going to ask, okay, I'm going to look at a small change in x, leave y constant, minus f of x comma y, all over x plus h minus x. It's exactly like we did back in 16a, except we now have a function of two variables. So this is similar to when we were trying to find f prime of x, and we did the limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x. Same idea, we're just have a function of two variables now. Okay, so we're actually going to write this out. So we're going to write this as the limit as h goes to 0, f of x plus h comma y. We're just going to plug in x plus h for x and y for y. So we're going to get 5 times x plus h squared times y cubed minus f of xy, which is just 5x squared times y cubed. All over x plus h minus x is just h. And just like before when we were doing this, the goal is to make that h cancel out the bottom, which means first we have to be able to factor out an h from the top. So right away, I'm going to factor out a 5y cubed from both of these. I'm going to get the limit as h goes to 0. I factor out a 5y cubed. I'm left with an x plus h squared minus an x squared all over h. Let's multiply this out. The limit as h goes to 0. Notice that the 5y cubed is just acting like a constant multiple. We could even bring it out in front of the limit if we really wanted to, but we don't really need to. So we got 5y cubed times x plus h squared is x squared plus 2xh plus h squared minus x squared all over h. And now we see that in this expression, the x squareds cancel, and we can factor out an h. So we've got now the limit as h goes to 0 of 5y cubed times, oh, I forgot to factor, let's factor out the h. So 5y cubed times h times the 2x plus h. Seem good? Now we can cancel that h that was in the bottom. And now we've got the limit as h goes to 0 of 5y cubed times 2x plus h. That h is going to go to 0, and we're going to get 5y cubed times 2x, which I would then write as 10xy cubed. Because we have a natural preference to write things in alphabetical order if we have the option to. Or as some people like to say, lexicographic order, which just means alphabetical order. We could also find the partial with respect to y in the same sort of way. It's going to be a little more terrible, but not a lot. So I think it's worthwhile, and then we will move on from this. And feel free to throw in questions if you got them. If I want to find del f del y, it's going to be the same idea, except now it's going to be the limit as h goes to 0 of f of x comma y plus h minus f of x comma y all over y plus h minus y. Yeah, the partial, yeah, exactly. Yes, you said it exactly right. And you can also say it as del f del y. So if you want to actually read this the way it's written, people write this as del f del. I have to write it over it. I can't even not, like del f del y. You don't say the over part, but I just can't not write it that way. I don't know why. Okay, so same idea. Oh, and let's write our function up here just so it's not lost on the page. Our function was 5x squared y cubed. So we're just throwing x in for x and y plus h in for y. So we're going to get the limit, h goes to 0 of, so 5 x squared times not y, but y plus h cubed minus 5x squared y cubed all over h. And just like last time, we can see that the thing that is the variable that we're not differentiating with respect to, in this case, x, all the x things are just going to factor out super easily. It might be different, like there might be some other functions where it's harder to see that, where you've got like if we were doing like sine of x, y, it'd be a lot harder to like factor out the x or the y or make it work, but it's still possible. So here, it's going to be the limit as h goes to 0 of 5x squared times y plus h cubed minus y cubed all over h. And just like the other time, we're going to be able to expand this out and cancel the things that don't have h's. That's going to be the limit as h goes to 0 of 5x squared times y plus h cubed is y cubed plus 3y squared h plus 3y h squared plus h cubed and then minus y cubed. And then we can cancel the y cubes. And then everything remaining has an h in it, so we factor one h out. So we rewrite this as the limit as h goes to 0 of 5x squared times h times, I'm left with a 3y squared, a 3y(h) to the first, which I'm just going to write as 3y(h), and an h squared all over h. H is canceled. So we're now left with the limit as h goes to 0 of 5x squared times 3y squared plus 3y(h) plus h squared. And all the things with remaining h's in them, those are going to go to 0 because h is going to 0. So we're left with 5x squared times 3y squared, or as I would probably simplify it, 15x squared y squared, which is exactly what we would get if we just took the derivative with respect to y and said, oh, it's going to be 5x squared times 3y squared. Exactly that. So definitely, you're probably not ever going to be asked to actually do a partial derivative the long way, but it's not really any harder than doing it way back in 16. Not that it was always easy in 16a, but it's the same process. Okay, that said, taking partial derivatives isn't too challenging, but you just have to, it's the hard part is to make your mind see the other variable and be like, oh, that's just a constant. So let's look at a few examples. Let me grab my examples here. Yeah. Sure. So let's look at something that's not too funky here. So let's say we've got f of x comma y equal to, let's say we've got x to the 7th plus y to the 4th plus x to the 6th, y to the 9th. And we're going to find not just the first partial derivatives, but also the second partial derivatives. So we're going to find, I think, like 6 derivatives. So we're going to find the first partial derivatives, which I'm going to write down. I'm going to write down all the things first, and then we'll find them. The first partial derivatives are just either del f del x or fx, and del f del y, which is fy. And then the second partial derivatives, now people use some different language here. When I say second partial derivatives, I kind of mean always with respect to the same variable. So for example, the second partial derivative with respect to x is going to be either del squared f del x squared, or as we might prefer to write, fxx. And similarly, del squared f del y squared, or fyy. Just a note on this notation here, right? This del squared f del x squared really means the partial derivative with respect to x of the partial derivative of f with respect to x. You're just taking the derivative with respect to x and then taking the derivative of that again. But that's why the notation is del squared of f over del x squared, because you're kind of thinking of doing the del x twice. It's kind of funky. Same deal here. And then we also have the mixed second partials. Mixed meaning one of each x and y. Now this is where things get a little bit funky. So you could have del squared f del x del y, which means you do y first. So I'm going to write this as del x of del f del y, meaning I would do the partial of f with respect to y first, and then the partial of that with respect to x second. And here's where the notation kind of sucks. We often write this, we do write this as f y x, right? So this notation here means y first, x second. This means the same thing. Y first, x second. And when I say y first, x second, I'm saying differentiate with respect to y first and then x second. And then, of course, also the other one, del squared f del y del x, which is f x y. Cool. So let's now actually do it, which I didn't leave myself enough room for at all. So let's go to another piece of paper here. Let me write down the same function here. So I think it's good to be comfortable with both notations. You will probably certainly see both. You'll most likely see both. Just like we often write down, like you might write down in your 16th class df dx, or you might write down y prime, right? We kind of use them interchangeably. So let's write down the shorter notation. So let's see. So first partials, fx is going to be 7x to the 6th plus 0 plus 6x to the 5th times y to the 9th. And sometimes it's totally fine to leave things unsimplified, but if you know you're going to be taking more derivatives later, it's usually worth your while to simplify. There's not really any simplifying to do here other than not writing the 0, but I would probably write this as 7x to the 6th plus 6x to the 5th y to the 9th. And let's find fy over here. Fy is going to be 0 plus 4y cubed plus x to the 6th times 9y to the 8th. And simplifying just a tiny bit, I would write this as 4y cubed plus 9x to the 6th y to the 8th. And let's go ahead and box those so we can see them for later. Typically, after I find the first partials, I then like to find each of the second partials in the same way. Because, well, the reason we're talking about second partials is because we're building up towards being able to find, to find relative maximum and minima of these functions, and it requires using the second partial derivatives. So fxx partial of this with respect to x is going to be 7 times 6 is 42x to the 5th. Plus 6 times 5 is 30, x to the 4th, y to the 9th. And fyy, let's see, if we differentiate 4y cubed with respect to y, we're going to get 12y squared. If we differentiate 9x to the 6th, y to the 8th with respect to y, the 8 comes down and multiplies the 9, and 9 times 8 is 72, x to the 6th, y to the 7th. Now here's where I think things get kind of interesting. So here I'm going to find fxy. I'm going to take the derivative with respect to x and take the derivative of that with respect to y. So sometimes I find it helpful to write this as del y of fx. Meaning I'm going to take the partial derivative with respect to y of 7x to the 6th plus 6x to the 5th, y to the 9th. And the derivative of the 7x to the 6th part is going to be 0. And the derivative of 6x to the 5th, y to the 9th, well, that x to the 6x to the 5th is acting like a constant. I'm going to get 6x to the 5th times 9y to the 8th. Which I'm going to simplify as 6 times 9 is 54. So 54x to the 5th, y to the 8th. and that's equal to fxy, or so now let's do the same thing, but let's find the other mixed partial fyx. So I'm going to start with fy and think of taking the partial derivative with respect to x of that fy. That's the partial derivative with respect to x of my 4y cubed plus 9x to the 6th, y to the 8th. We take the derivative of that. The derivative with respect to x of 4y cubed is going to be 0. And the derivative with respect to x of 9x to the 6th times y to the 8th, although basically we're just taking the derivative of x to the 6th and leaving everything else alone. So we're going to get 9 times 6x to the 5th times y to the 8th. And you'll notice, well, actually, I'm just going to write the answer. 9 times 6 is 54. That's 54, x to the 5th, y to the 8th. And that's what my fyx is. I'm going to ask you, Caroline, what do you notice? They're the same. Now, here's what's generally true. Generally, I don't know, generally, maybe not, generally or typically, it is going to be the case that the mixed partial with respect to x first and y second, which is going to equal the mixed partial with respect to y first and x second. Right. So I should point out, this is not always true. But it is generally true for normal functions. True for quote unquote normal functions. What do I mean by normal? I mean something that isn't contrived. Basically, anything that you see that looks like just f of x comma y equal to some powers of x or sine or cosine or is going to meet this criteria. I'll just let me see if I have the example that I'm looking for. If not, I will grab it really quick because I do think it's worth mentioning. So let me just mention an example where this doesn't work, not because we're going to explore it, because I want you to kind of see the simplest example that I'm aware of a function that doesn't meet this criteria, and then you'll see what I mean by normal. Sure. Sorry, 1 second. Because I never remember what this function looks like because it's, let's see here. 1 moment, please. In here. No, let's look over here. All right, I should have planned ahead for this. There we go. Okay, so again, I don't want to get too deep into this, but I will point out. So here is an example of a function where these partial derivatives, fxy, these mixed partials, fxy and fyx are not equal to each other. And this is I should point out, this is probably the simplest example I know. Here it is. It's f of x comma y equal to the piecewise function x times y times x squared minus y squared over x squared plus y squared, as long as x comma y is not equal to 0 comma 0, and it's equal to 0 if x comma y is equal to 0 comma 0. So now maybe you kind of see the point I'm making in that anything that's, if this is the easiest example of a function where this doesn't work, then anything that looks normal, where you're just like adding, subtracting, multiplying stuff together, is going to work out. You really have to, your function really has to be some sort of piecewise mess to even have a chance of this not equaling each other. So normally we don't really worry about these two things not equaling each other. And specifically, we are generally expecting them to be equal to each other. So if you're doing a problem and you've taken partial derivatives, mixed partials either in either order, and they're not the same, it means you probably made an error. And it's worth going back and looking at what's going on. Yeah, we certainly, if anyone is interested in me discussing this somewhere later, I'll post the example of this further so you can actually see why it's not true. But I don't think it's something we need to sweat too much in this class. Cool. So let's look at some more examples. Yeah. That's never my favorite example. Oh. Yeah, let's go ahead and go. One second. Got more examples over here. Sorry, I just want to find things that are not too awful. Yeah, let's look at that. Sure. Let's say our function, let's look at something that's kind of not so awful. Let's look at our function being f of x comma y equal to e to the x squared plus y to the negative third. Let's focus that up a little bit. Or not. It's kind of, I feel like we're getting a little, oh, you know what, it's the HVAC. It makes it a little bit. Yeah, is that really all? Is that as good as it's getting? Maybe, can we focus on my hand maybe? There, I guess that worked. Okay, great. Maybe, okay, fine. So here's our function. You could kind of attack this one of two ways if you're taking partial derivatives. So we want to find del f del x. One way is just to think of it as is. So I've got e to the stuff, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff. What's the derivative of x squared? What's the derivative of y to the negative third? Right? But no, but I wanted you to say that. It's easy to get tricked because when you start thinking of the chain rule, you start thinking of the derivative of the inside stuff as just the normal process. But we still have to be in the mindset that y is a constant. So it stays here because the derivative of e to the stuff is e to the stuff, no matter if that stuff is, constant, variable, whatever. But once we multiply by the derivative of that stuff, then we have to be like, oh, it's that. So that's going to be 2x times e to the x squared plus y to the negative third. Now, one way we could have maybe, this isn't always an option, but one option we could have maybe explored is we could have rewritten this as e to the x squared times e to the y to the negative third. That would have been an option. And then if we'd taken the derivative, we could have been like, oh, the derivative is going to be, well, the e to the y to the negative third is just a constant that's going to stick around. So the derivative of e to the x squared is e to the x squared times 2x. And then that constant just stays around. And that's exactly the same as that. It's just written a little differently. So sometimes you can simplify things before differentiating to make it a little easier. In the same sort of way, we can find del f del y by saying, well, again, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Now the derivative of x squared is, and the derivative of y cubed is exactly what you said before, negative 3y to the negative fourth. And so I would write this as negative 3y to the negative fourth times e to the x squared plus y to the negative third. I might put parentheses around my exponent there just to make sure the person reading my work knew that I was putting that in the exponent. Okay, when you start taking second derivatives, it gets messy. So if I'm going to take del squared f del x squared, which is just the derivative of, it's the derivative with respect to x of the derivative with respect to x. So I'm going to take my del f del x and take the derivative of that. I usually like to write out an additional step here, meaning I kind of like to write this as the partial with respect to x of the partial with respect to x that I just found. I'm going to take this here, right, my del f del x. I'm just going to plug that in right there. So I've got 2x times e to the x squared plus y to the negative third. And then, excuse me, I'm noticing that I have a function of x times a function of x. which means we're gonna have to use what? Exactly. So this thing's got like little hairs on it. It's terrible. Okay, so derivative of the first part is 2x. Sorry, is 2 times the second part, leave it alone. X squared plus y to the negative third. Plus, then we flip it up. We leave the 2x alone. And we multiply by the derivative of e to the whatever, and the derivative of e to the stuff. So this is where I like to use the work I've already done. I know that the derivative of e to the x squared plus y to the negative third with respect to x is exactly 2x times e to the x squared plus y to the negative third. So I can just write another 2x times e to the x squared plus y to the negative third. And if I didn't have to take any more derivatives, I would probably just leave it like this. If you wanted to, though, I should point out you can factor this. So this would factor, if I factor out, let's say I can factor out a 2e to the x squared plus y to the negative third. Times, I'm left with 1 there and 2 times x there. We don't often do this, but sometimes we are trying to like maybe find where the second derivative is equal to 0, and so factoring as much as possible is sensible. Let's look at the second partial with respect to y. So del squared f del y squared, which is del y of the partial with respect to y, which was this negative 3y to the negative fourth of e to the x squared plus y to the negative third. The same sort of thing is going to happen. We're going to use the product rule. And I typically, if I've got a product rule and there's some constant in front, you can bring the constant all the way out in front, like the negative 3 all the way in front. But I kind of like to just group that with the first, or whichever piece seems like simpler. So I'm like thinking of this as one piece and this as another piece. So when I take the derivative of negative 3 y to the negative fourth with respect to y is going to be positive 12 y to the negative fifth times the other piece left alone, plus, and then we switch it up. And we can do the same thing we did last time. We can leave the negative 3 y to the negative fourth alone. And we know that the derivative of this second piece is the partial with respect to y that we already found originally. So the derivative of e to the x squared plus y to the negative third is e to the x squared plus y to the negative third times a negative 3 y to the negative fourth. And I don't really want to, so I'm not going to, but we could do some simplifying here by factoring if we really, really wanted to. You could factor out an e to the x squared plus y to the negative third. You could also factor out a y to the negative eighth. Seems weird, but yeah.
So those are 4 answers.
Well, right, but we want one more. Well, we actually want 2 more answers, but we're only going to do one of them. We also want the mixed partial. So we're going to find del squared f del y del x. Okay, so let me ask you. When I write it this way, it means I did which one first, the x one or the y one? Right. So I'm gonna write this as del y of the x one, which was this. Yeah, that looks. Oh, I wrote it weird there. There's this one here. 2x times e to the x squared plus y to the negative third. And what I want to point out is I don't have to use the product rule here, because that 2x, if I'm differentiating with respect to y, that 2x is just acting like a constant. So that constant's going to hang out. And then I multiply by the derivative of e to the stuff with respect to y. So I'm going to get e to the same stuff times the derivative of that stuff, which is what? Perfect. Awesome. And then I would probably simplify and write this as negative 6x y to the negative fourth times e to the x squared plus y cubed, plus y to the negative third, sorry. And what I want to point out is what you should do later, or what people watching the video should do, take a pause and do it, is find the mixed partial in the other direction and see that it's the same. So I'll just try to squeeze in here that this is also equal to del squared f del x del y. But you should check that on your own for sure. Good practice. Okay, let's see. Where else do I want to go here? That's a good example. We really want to do that. Oh, let's look over here. Sorry. We got all sorts of examples. Let me make sure we're doing. Yeah, let's look at. Sure. Where are we going next? Are we already going? I'm just trying to think about where we're going next. I think we're going to relative extrema already after this. Yeah. Did you talk about it already? Like talk about. Okay. Sure. We can. Yeah. Let's actually. I know we should do a couple things. Okay. Where does that go? So I should point out, you can do this for more variables, right? You could totally have a function of not just two variables. For example, you could have something like f of x comma y comma z equal to x squared times sine of 5y plus 4z cubed. And be asked to take any partial derivatives we are thinking about. So we could find the partial with respect to x, which is going to be 2x times that constant. Right, as far as x is concerned, sine of 5y plus 4z cubed is a constant. Or we could find the partial with respect to y. Now the x squared is a constant. And we have to multiply by the derivative of sine of something with our variable in it. So what's the derivative of sine of some stuff? Not sine. Right, cosine of the stuff. And what's the derivative of the stuff? Right, thank you. Good. I was trying to trick you a little bit, but you didn't fall for it. And then I would probably write this as 5x squared times cosine of 5y plus 4z cubed. In a similar way, we could find the partial with respect to z. Again, x squared is a constant. The derivative of sine of some stuff is cosine of the stuff. But now we have to multiply by the derivative of the stuff, and the derivative of the stuff is what? Right, good job. And then I would probably write it as 12x squared z squared times cosine of 5y plus 4z cubed. And you can find all sorts of second partials or third partials or mixed partials, right? Like you can do all sorts of bonker stuff. Like someone could ask you to find, f. I'm going to make it kind of stupid. Yeah, someone can ask you to find something like f x x y z. I don't really want to do that, but this would just mean do the derivative with respect to x first, then do it with respect to x again, then do it with respect to y, then do it with respect to z. If someone was going to write this, that'd be terrible. If someone was going to write this in the other notation, I don't really love it, but you would be del to the fourth of f. You're doing 1, 2, 3, 4 derivatives. And what are you doing first? And then what are you doing next? Right, so it'd be, you could write it, right, del x, del y, del z. It's kind of dumb looking. And you'd probably even combine, someone would probably actually write this as del z, del y, del x squared, because there's two del x's there. But yeah, it's dumb. But then we could do it, right? fx we already found. So then I would then find fxx, which would be the partial of this with respect to x. It'd be 2 times sine of your stuff. And then we take the partial of that with respect to y. You just kind of keep adding on the next derivative. So the derivative with respect to y is going to be 2 times cosine of your stuff times the derivative of your stuff, which is 5, which is definitely in our interest to simplify. It's not a lot of simplification, but it's worthwhile to make it so your next derivative doesn't suck. And then the partial of that with respect to z. And I'm surprised I was able to pick one that didn't just turn out to be zero, because a lot of times, right? For example, if I threw in another partial with respect to x, I'd be done because it'd be zero, and then there wouldn't be anything else to do. But here it's going to be 10 times the derivative cosine of some stuff is, yep, negative sign of the stuff times the derivative of the stuff, which is right. So in the end, I would write my answer as negative 120 z squared times sine of 5y plus 4z cubed. So just the point being that you can keep taking partial derivatives in any, like you can do as many as you want. Usually we're pretty limited to like just doing the first or the second or the mixed ones, but you could feasibly do a whole large number of them in kind of whatever order.
So you box that one.
Because that's my final answer. Because that is what f x x y z is equal to, which is what I started, which is what I asked for in the beginning. But the process was to do each one, right? I first did fx, then I did fxx, I did fxxy, I did fxxyz. So every time I'm finding the next partial derivative, I'm just looking at the previous partial derivative and differentiating that with respect to my next variable. So, right, I should point out, just to kind of see, right, this was the partial with respect to x of fx. And this was the partial with respect to y of the fxx I had found in the previous step. And this here was the partial with respect to z of the fxxy I had found in the previous step. So every time I'm finding the next partial, I'm just taking the partial derivative with respect to the right variable of the previous partial derivative I'd already found. But usually it's just like one or two steps because we're really usually finding second partials at the most. You know, I love that example, even though it's perfectly fine. Let's go ahead and I feel like we can move forward just a tiny bit, or at least start talking about. Because so here's where we're gonna go. Oh, yeah, fine. I have some good pictures, but they're not here. Maybe let me just show you one thing that I think I know what I want. I can grab a picture. Where are you, picture? Not in the right place. All right, then. There's usually a thing here that I'm used to seeing. Sorry, one moment. I think that's it. Oh, there we go. So the other thing I really wanted to point out is that if you're so these functions of two variables typically are often describing like a surface in three-dimensional space. For example, if you were looking at the function f of xy equal to, let's pick something not terrible, James, something basic like x squared plus y squared, that's what we call a paraboloid. It opens upwards. And people often draw this by looking at the traces, which I'm going to mention just briefly. So the trace is what you get by setting one of the variables equal to 0. So if you set x equal to 0, x equal to 0, that means you're in the YZ plane. Right? If x is 0, you haven't moved this direction or that direction. So you're stuck in being y being whatever or z being whatever. And in the YZ plane, if x is 0, my f of just 0 comma y is going to be y squared. Or in other words, z equals y squared, because we're thinking of this as our z. That's just a parabola. Usual upward opening parabola. Looks like that. Oh, that's a good parabola, James. Nice job. But sometimes like, oh, I drew that better than I thought I could. And then if we look at the trace when y equals 0, which is going to be in the xz plane, we're going to get z equal to x squared, which is also an upward opening parabola, but instead of the yz plane, it's in the xz plane. So it kind of looks like it's coming out towards you, which I'm less good at drawing, but I'll do just fine here. And then it's not super helpful in this particular problem. If you look in the trace in the z equals 0, where we're in the xy plane, or I like to think of as the floor or the ground. Well, then we get 0 equal to x squared plus y squared, which only has one solution when x and y are both 0. It's just the point, which certainly is what you get in the xy plane. It's just not super helpful graphically. So this shape looks like, well, I mean, it is what we call a paraboloid. Basically, a parabola just revolved around. I feel like sorry, I missed that little part right there. That looks a little better. A parabola revolved around the z-axis. And notably, this paraboloid has a minimum value, right? That value right there, the minimum value of z equal to x squared plus y squared, or if you prefer, f of x comma y equal to x squared plus y squared, is z equal to 0 at the point x comma y equal to 0 comma 0. Right? That's the minimum value. There is no lower z value. And the thing to observe here, which is what I wanted to point out with this drawing that I didn't want to actually draw myself, is that you get these maximum values or minimum values, or what we call saddle points, when the tangent plane is horizontal, right? If you look at that maximum point there, the tangent plane is definitely a horizontal plane. Same for the minimum, same for the saddle. But the tangent plane being horizontal means that the derivative in the x direction has to be 0, and the derivative in the y direction has to be 0, because you can't be going up or down, otherwise your tangent plane won't be horizontal, it'll be slanted in some way. So what that ends up meaning is that the way we find these potential places where we have either a maximum or a minimum or a saddle point is by finding critical points where both the derivative with respect to x and the derivative with respect to y are equal to 0. Which is totally true in this example I was just showing you. Right? If I wanted to actually, sorry, can I close this? Maybe, not ever. If I actually wanted to find the critical points for this, I would find them by taking my partial with respect to x, which is 2x, and setting equal to 0 and getting x equal to 0, and my partial with respect to y, which is 2y, and setting that equal to 0 and getting y equal to 0. So here my only critical point is the point 0 comma 0. And then we do a little bit more work to figure out whether it's a maximum, a minimum, or a saddle point, or potentially none of them, I guess. None is an option, but it's a weird option. Yes, we have time for one example. So let's look at one straightforward-ish example. Sure, maybe. Let's look at this example. I would love it. Did I not give myself the example I wanted? Not. Just trying to think about it. This example is really, that's fine. Okay, sure. So let's say we have this function. F of x comma y equal to x cubed minus 3xy plus y squared. And I want to first find the critical points. And I should mention, there might be one, there might be many, there might be none. It's possible to have no critical points. But the process is always to set each partial derivative equal to 0. So let's take the partial with respect to x. I should say each first partial derivative. So take the partial with respect to x, we get 3x squared minus 3y. Set that equal to 0. Take the partial with respect to y. Get 0 minus 3x plus 2y equal to 0. And this example is harder than I meant. It's not like super hard, but it's definitely a little harder than I meant it to be. I would love to go back. Let me go back and let's table this example. Just not that we couldn't do it, but I want to start off with an easier example. Let me just grab this thing I had before. 1 second. I do want to give you one example before we end for today. Yeah, here's a better example. Let's say we had, for the function f of x, y, we have x squared plus y squared minus 2x plus 4y plus 3. Yeah, sorry. there's our function. And now we want to find the critical points for this. So my partial with respect to x is 2x minus 2. My partial with respect to y is 2y plus 4. And we're going to set each of those equal to 0. Setting 2x minus 2 equal to 0, we get 2x equal to 2, which gives us x equal to 1. Setting 2y plus 4 equal to 0, we get 2y equal to negative 4. We get y equal to negative 2. So our only critical point is the ordered pair 1 comma negative 2. The critical point, so just like in 16a, the critical point is where we might have a relative maximum or a relative minimum. In 16c, it's where we might have a relative maximum or a relative minimum or potentially a saddle point. Because back to that picture I was showing you, the critical point, oh my God, maybe ever. The critical point is where both the fx derivative is 0 and the fy derivative is 0. Meaning it's the only place where we could have a tangent plane, which is where we might have a maximum or a minimum or a saddle point. But I want to stress here that you have to have both of these derivatives equal to 0 at the same time. Meaning this is the only point where that both of those are 0, right? You couldn't have like 1 comma 5, because while 1 here makes that derivative 0, 5 doesn't make that derivative 0. And we should table the discussion for how to check if it's a max or min because we've run out of time. But I just want to show you because I think it's nice to see. You can look at, where's my phone? Student was showing me, so there's a couple of different websites you can use to graph things three-dimensionally if you care to. And my student the other day showed me one I had not seen before, which was math3d.org. I thought it was kind of cool. I haven't used it very much. I don't actually know. But if we look at math3d.org. You can, so if we want to I think we need to graph an implicit surface. I've never used this before, apologies. No, maybe. So anyway, you should play with this because it's probably maybe that. There. I want to add this is an unstable feature. Fine, we'll deal with it. So we want our equation to be z equal to, and then our function was x squared plus y squared minus 2x plus 4y minus 4y plus 4y minus, plus 3. Yeah, okay, that's cool. And you can see that on this thing, maybe you can see there is the point there, and that point is, believe it or not, where x is equal to 1, right? X is 1, and go from the back here, y is equal to negative 2. So you can kind of see that, at that point, we've definitely got a relative minimum. It's kind of neat. The other one I like is GeoGebra 3D calculator. That one's also good for graph. Again, you don't need to graph any of these using this. It's just kind of, it's nice every once in a while to kind of see the thing that you're actually finding the relative minimum of. So you can totally check this out if you want to. It is not at all necessary though. But both of those are good sources. All right, next time we'll talk about finding these critical points for more complicated examples and also how to see if they're a maximum or a minimum or a saddle point.